Good morning, everyone. I'm Niranjan Prabhu, PhD student, a joint PhD student of Politecnico di Milano and Ghent University, Belgium. And also my project is under Smartings ITN network, which is funded by European Union under Marie Curie ITN network. Today, I'm going to present experimental methodology to assess fatigue behavior and fatigue damage recovery by autogenous self-healing of ultra high performance concrete. So I begin with a little brief introduction about what is exactly self-healing is. Then I proceed with the fatigue test. So what exactly is self-healing concrete? So ability of the concrete to repair its cracks autogenously or autonomously, so without any human intervention. So yeah, autogenously is the concrete which has innate ability to heal the crack width by itself. Then autonomously is we specifically engineered the concrete with some capsules or vein type vascular network type self-healing agent. Yeah. Then why we need self-healing in concrete? So what are the advantage of using self-healing? So where it can able to applicable? Especially the crack with less than 300 micrometer. So yeah, the most of the self-healing we are aiming to heal the crack within 300 micrometer. So these kind of cracks are unavoidable, and also it is not that much risk to concrete in the short term, but in a long term it will affect the durability of the concrete, and it might affect repair works, and we need a lot of maintenance work. So main objective of the self-healing is to improve the durability of the structure, at the same time reduce maintenance and repair cost. There are a lot of types of self-healing agents, like I explained in first previous slide: autogenous healing and autonomous healing. 1 minute, I will turn on the pointer. So UHPC usually falls under autogenous healing, but sometimes we add admixtures, so which act as catalyst for this healing. So then if act as a catalyst, then it is stimulated autogenous. Then in autonomous healing, we have like micro encapsulation, macro encapsulation, vascular healing, then bacteria based concretes. So most of the research is based on autogenous, because we are using UHPC concrete. UHPC concrete is innate ability to heal on its own. Then I'm using a crystalline admixture so that it will heal effectively in a very quick short duration. Then what are the process involved during those healing? So we have three different process: physical process, chemical process, and a mechanical process. In physical process, swelling is the main criteria. Swelling happens, it's actually very small, mostly in like micrometer, nanometer to micrometer. Then chemical process is continuous hydration. So continuous hydration usually like happens up to like a year or two in most of the concrete. Then calcium carbonate precipitation. Then in mechanical process, actually during the cracking process, there are like the broken debris which is stuck inside the concrete, and it helps to seal the cracks very quickly. And also there are particles from water. This also helps in sealing concrete cracks. Okay. So now I begin with my experimental plan. So initially we tested monotonic test, just a 4-point bending test, to assess what is the physical characterization of our material. Then we begin with the preliminary analysis. In preliminary analysis, we took 3 different crack width: 0.05 mm, 0.25 mm, and 0.45 mm. Then we also have another set of matrix. The load range varying from 10% to 50% effort. I will explain later what is effort is. Then 10 to 70% effort, and 10 to 90% effort. So based on 3 different pre-crack width and 3 different loading range, we pick one from each to evaluate our fatigue performance, self-healing fatigue performance. So it's mainly we picked 0.25 mm crack width because the crack width is close to serviceability limit condition, and we picked 10 to 70 range because this within this low range, our specimens fail like within 2 million range, 1 to 2 million range, because the 2 million is at 5.5 hertz frequency. It will take about a week to test a single specimen. So we can go only up to 10 to 70% range. We can't go below less than 10 to 70% range. If we go to 10 to 90% range, then the specimen fails very quickly. So we thought it might affect our observation on self-healing progress. We may not able to obtain very clear distinguish between healed and unhealed specimens. So yeah, because of that, we choose the 10 to 70%. And then later we changed 10 to 80%. It's because of the fiber content. We observed there is a slight change in the fiber content in the specimens we tested later onwards. So we shifted to 10 to 80%. Then the pre-crack is so initially we cracked the specimens up to 0.25 mm before the fatigue test. So that is pre-crack. So that then we go for pre-fatigue. So the pre-fatigue is 10% to 80% effort. So the pre-fatigue is we do a certain number of cycles, then take out the specimen, put it in water for healing for some duration, 1, 2, 3 and 6 months. Then we take out the specimen. Once again, we put it in fatigue machine and we test the specimen up to failure or up to 2 million cycles. So the pre-fatigue is we choose two threshold, COD 1 mm or 700,000 cycles, whichever reaches first, that is pre-fatigue. Then the specimens from the pre-fatigue, we tested up a few specimens under 4-point bending test to check what is the residual flexural strength after 700,000 cycles. So we observed almost it is there is no change in flexural capacity before and after pre-fatigue. It's almost the same. Then we put specimens, we tested specimens after 1 month and 3 months in submerged condition. Then the post, then once again, we put it in cyclic machine. That criteria is up to 2 million cycles. After 2 million cycles, we did once again 4-point bending test. Then a few specimens we took out of water after 1 month. Then after 2 months, in between we did the fatigue test in order to check whether our material can able to heal repeatedly upon damage. Then also we observe healing progress through UPV and microscope. So microscope is mostly give the surface crack closure. Then UPV will give the healing, a good healing progress after each interval, 1 month, 3 months, and 6 months. So the specimens, we prepared it from the slab. So the main objective we choose this way is to have realistic condition, because if we do the specimen of dimension 500 into 100 into 20 thickness, the fiber tend to orient along the longitudinal direction. That is the best case, but in reality that is not the case. So the fiber will orient in all three directions. So we first cast the slabs and we measured the fiber distribution, and we cut down the slab with the dimension of 500 and 100. We matched the orientation of cutting the specimen based on the fiber distribution. So it should be like at least uniform fiber distribution in single specimen, should not be vary. So that's the objective. And also the specimens are like 1.5 year old at the time of initial pre-crack. So the long-term hydration won't come in healing. So yeah, it's more like mostly we want to stimulate a realistic condition. Okay. So on the left, this are the specimens we tested. So for 1 month, we have 3 specimens in all, at least 3 specimens in all criteria: 1 month, 3 month recrack, and a pre-fatigue monotonic test. So on the right side, the first curve is a pre-crack. So this curve is 0.25 mm crack width. Then the following blue one is pre-fatigue. So this is gone up to 700,000 cycles. Then we allowed these specimens for a month. Then we rerun once again the fatigue test, and we observed what are the changes happened after the 1 month healing or 3 month healing. So yeah. So this table will give detailed about how many cycles we ran during pre-fatigue. For example, the N02 is 700,000 cycles, N51 is 182,000 cycles. So this means the N52 reached that 1 mm crack width under load before 700,000 cycles. So we used another criteria to stop the free fatigue limit. And also the another important thing is the number of crack widths. So we observed the crack width between like 10 to 36 number of crack width within 20 centimeter length. Then after the healing period, we once again rerun the test. So the specimens which already like 1 mm crack width under load, those specimens are failed very early. The specimens which we ran 700,000 cycles during the pre-fatigue, it crossed more than 2 million cycles. So we stopped the test at this point to do a 4-point bending test. Then we also counted number of fibers because the fiber play very crucial role in fatigue life. So we observed the fiber variation is anywhere between like 450 to 650 fibers along the cross section. Yeah. So the major parameter we evaluate is based on the stiffness. So whether the stiffness increases or reducing, and also this will give clear picture about the changes happening in individual specimen. For example, if you noticed 3-month specimens before healing, we have the stiffness like 11.63. Then after healing, the stiffness got increased. So we observed in both the specimens before and after healing, the stiffness got increased for 3 months. But for 1 month, we noticed the stiffness got reduced. It's the phenomenon is happening just in opposites. You can also see in the graph. For a 1 month specimen, the stiffness reduced, and a 3-month specimen, stiffness increased. So it shows we definitely need at least minimum 3-month healing period in order to increase the stiffness. And also why the stiffness is important is we after this stiffness evaluation, we evaluating rate of crack opening. So for that rate of crack opening, okay, I will explain the left graph. So usually we do first initial pre-crack. This FL is the maximum flexural strength. Then the place where we started to unload is a residual load after 250 micrometer. So the residual load is FR. So the fatigue loading criteria is like 10% at the bottom level, 10% FR. Then the top maximum fatigue criteria we took here is 80% FR. Then only with the top flexural load and corresponding COD. So we plotted those COD versus cycle is the top COD versus number of cycles curve. Then we polynomially draw a curve fitting. So based on the curve fitting, we find out rate of COD versus a COD graph. So the rate of COD is COD B minus COD A divided by B minus A. So it will give clear picture. Actually, this is like a 3-part of the curve. One is like a stable. Sorry, yeah. The initial part of the curve is a stable part of the curve. Then it will clearly show the critical point. Then after the critical point, we have unstable part of the curve, and also it helps us to design the fatigue structures before the critical point. So here we are evaluating what is happening in this stable part of the curve, and also the critical COD. So whether the critical COD is reducing after 3 months or increasing after 3 months. So that is what we are interested in. So especially for a 3-month curve, after healing, the stiffness got increased, and also the rate of COD got reduced. So for specimen N01, the rate of COD reduced like 20 times, and also in 21, the rate of COD reduced 3 times, around approximately. So yeah, so it clearly shows very significant changes happening in UHPC FOC concrete in fatigue life. Yeah, and also in 1 month, we noticed very slight difference among before and after healing, but yeah, it is in opposite side. So it got slightly increased. Sorry for that. Then UPV and microscopic image analysis we did. The +1 is uncracked, so this is at the initial before a pre-crack. Then the brown diamond is after the pre-crack, so the UPV velocity got reduced. Then after free fatigue, it reduced further. Then after 1 month healing, it approximately reached close to the uncracked level. Then 3 months is further it got healed. So the same thing we observed in the surface crack closure. The surface crack closure we observed is initially here it is like 0. So the total crack width it's yield anywhere between like 60 to 100% in 1 to 3 months. Yeah, the summary is the specimen stiffness increased during the healing period, which reduces the rate of COD by as much as 20 times. Then upon a repetition of cracking and healing, the healing capacity is likely persisting in recycled UHP FOC specimens. Such healing capacity is able to recover the damage induced upon recracking. So the experiment is not completely finished. Still, we have 1 month worth of experiment is pending, especially the 6 month, and a few of force fatigue are still pending. So yeah, still we get to find out a lot of interesting about this experiment, and also we couldn't able to calculate directly the fatigue life difference before and after healing. So we're planning to do indirect calculation of fatigue life variation before and after healing. Yeah, thank you.